Awesome. All right. Welcome, everybody. My name's Peter Hansen, organizer of the DataEng meetup. We've got two fantastic talks coming to you tonight from the Microsoft Reactor. We don't have anyone from Microsoft Reactor here present, but I was going to say a really big thank you to all of you folks at Microsoft for hosting us tonight. The pizzas are delicious, even better when you're actually tasting them in real life, rather than just watching it virtually over the interwebs. So yeah, it's really great to be back here in person, sort of chatting with you all. We've got, as mentioned, two awesome talks tonight. Simon Aubury from Thoughtworks, also co-organizer of DataEng Bytes, and which is a good segue to DataEng Hack. We're doing a data engineering hackathon on the 28th of April. Tickets around $50. We've got a whole bunch of really awesome sponsors: Neo4j, Snowflake, Fivetran, Microsoft Azure, DBT Labs, Databricks, DataStax, ThoughtWorks, AWS, Imply, Microsoft Reactor, and a few other community sponsors. And yeah, so that's going to be really great fun, going to expose you to a whole bunch of really cool data engineering technology, and perhaps, also some hiring opportunities. I keep hearing the same thing from everyone: how do I hire more data engineers? So perhaps, getting along to that might help you find that really awesome job that you're after. Simon Aubury is going to be presenting about the data engineering around where his cat is sleeping. I'm sure he'll go into a lot of detail about that. Our second set of speakers for the night is Ari Sarana, Principal Data Systems Engineer at Nearmap, and Zoran Stojakovic. Sorry, is it nearly? Yeah. Okay, yeah, Senior Data Systems Engineer at Nearmap. They're going to be taking us through how to build more reliable data pipelines for Nearmap deep learning models. That sounds very complicated, but I'm sure they'll present it to us very nicely. So without further ado, I might just hand over to Simon to take it away. Thanks so much, Simon. Welcome.
Thanks, Peter. And thanks everyone for coming on today. It's 6 p.m. It's Thursday night. It's dark, a bit cold outside. this, and what kind of accuracy can we actually build out once we've actually put this technology together. So hardware, data platform, and prediction model. Thank you, Peter. So I have to start again now?
No, you're fine. Continue on from there.
It's all good.
Apologies for the slowly getting the hang of this.
Thank you. Cool. Alrighty. So let's talk firstly about how we collect the data. Now, this is really important because one of the important things for any good machine learning model is feeding it with a bunch of historic data. So I had a bit of a hypothesis here that I'd need about 3 months of historic data to actually build out a level of confidence with a machine learning model. So let's drill in briefly to the hardware that's actually necessary to firstly work out where Snowy is in the house, and also how we're actually going to gather the environmental conditions. So firstly, I want to know right down to the room level where Snowy the cat is at any moment in time. Now, cats aren't particularly good at data entry, and she's not very good at filling out a little notebook. And I don't want to walk around working out where she is historically. So I need to build out some sort of automated process to work right down to the room level where the cat is at any moment in time. So the solution I ended up with was I ended up putting a Bluetooth transmitter on Snowy's collar. You've probably seen them, those little Bluetooth tiles. I happen to use one called a tile. And what's really good about it is it's small, it's lightweight, and it doesn't actually disturb a cat who's wandering around the house. And it's just constantly sending out Bluetooth low energy signal with exactly the same code each and every time. So that's a little transmitter on the cat. But I then need to work out where the cat is within the house. So I used a whole bunch of stationary receivers. Now, for the gadget-minded, I'm using something called an ESP32, which is a super low-cost compute platform. And they're so cheap, they cost a couple of dollars each. I actually ended up buying 8. I put 6 in rooms of the house and 2 outside. Now, this combination allows me to work out where Snowy is by simply working out which receiver is receiving the strongest signal. And it's basically a tussle if Snowy is in the study, but also the receiver in the bedroom is receiving that signal. It's basically who's getting the strongest signal really is the tiebreaker of where Snowy is at any moment in time. So that's how to work out where a cat is. For environmental conditions, I also wanted to work out temperature and work out some other conditions, essentially whether it was raining or not. So I found that these things were super cheap. These are Xiaomi temperature and humidity sensors, and they connect to a Zigbee network, which is just a sort of a low energy protocol. So I placed 4 sensors around the house and 2 outside. And this gave me both an idea of the temperature and the humidity at various locations across the house. So this gives me an idea where Snowy is and what the climatic conditions look like. So that's the hardware. But getting the hardware is useless. We actually have to talk about what's the data platform that's going to support this together. So this is my rudimentary data platform, which is actually sitting in my home server. So all of those hardware components are communicating over a protocol called MQTT. And if you've used Kafka or Kinesis, that's the same sort of mental model. It's a very lightweight communication stream. And in my server, I've got Home Assistant and a Postgres database. So Home Assistant is an absolutely fantastic home automation platform. It's primarily a Python open source community, which puts together these really, really cool modules, which allows you to cherry pick some of these components. So it's really straightforward to do integrations such as Xiaomi integration and an equivalent Python package called ESP presence. So it allows me to collect all of this data together, and it acts as a good sort of bridge between the hardware components and the beginning of a data platform. Now, Home Assistant's great, but it's really polarized to helping with home automation tasks. They're essentially low latency tasks, and you don't actually need the data that long. Whereas I kind of wanted to flip that around. I wanted high retention, long duration collection of data and didn't care so much about the latency. So I flicked out its default storage, which out of the box is SQLite, and replaced it with Postgres, and changed the retention policy so I could actually capture this data over 6 months. the fantastic Home Assistant community have really, really great resources for these kind of substitutions. And to give you an idea about the data that's flowing through these, each of those sensors, you know, the 6 external sensors and the 8 ESP32s are each spitting out somewhere between 12,000 and 18,000 updates per sensor per day. So that's a lot of data flowing through here. So Home Assistant's just storing this basically in an internal table called a state table. And there's no thought about this. This is just recording into the state table every single time any of those sensors receives any information. So that builds up in a sort of a time-ordered sequence, but it's fairly rough and ready. And my goal is kind of like to take that long stream of data and do a bit of rudimentary data processing. So my goal is to really summarize all of those very, very noisy sensors and then pivot it out and actually do summaries per hour, but also correlate it sort of horizontally, pivot out the attributes. So I've got things like indoor temperature, outdoor temperature, and most prevalent location for each of those hours of the day. So classic data engineering task. So what's a classic data engineer going to do? I chose to use dbt. So if you've never used dbt before, think of it as a great way of structuring SQL jobs. So it's typically sold as the T in ETL. I think sort of another mental model is it's kind of like Terraform for databases. It's a really, really great way of solving some straightforward tasks. So my tasks here, I had a whole bunch of tables. I wanted to apply a number of sort of SQL functions to each of them, such as that analytic function. But I also wanted to be able to cope with late arriving data. So when I was training models on 1 month and then had some additional data coming through later, dbt gives me a really good mechanism for snapshotting data and then injecting that into my model later. So dbt is a great way of handling both the capturing of data, the incremental delivery of data, and also the summarization of data. And from my perspective, I can just concentrate on code like that and then get dbt to help with some of the orchestration. Extra bonus points, it does really nice lineage graphs, which is great if you're putting together a presentation. So, yep.
The sensors that you referred, and I can recall from the conversation, they are feeding hourly data?
So the question was, do the sensors spit out hourly data? No, they spit out data essentially every few seconds. So each sensor by itself is spitting out data roughly every half to 1 second. And so the goal of dbt is to take that avalanche of very, very cyclic data every second and condense it down to essentially aggregates for each hour.
On the top of it, I've noticed, I can be wrong also, on your table, the date and timings are on hourly basis. Like if you see 30th of...
So that's the raw data.
On the below table?
Yep, so you can see that that's right down to the millisecond, and that's my goal. My goal is to get data that looks like that. So good question. So once we've got that, so this gives you a bit of an idea about the best way of feeding a model is to like summarize the data down. And so my first task was to, now I've got all of this data sort of compacted down, kind of just wanted to test whether I actually had something to work with. So this is my first evaluation model. This was essentially just a really quick test of can I validate with any level of accuracy whether the cat is in my son's room or not in my son's room. So this is sort of like an evolutionary approach to building up data models. Can I test for something simple? And so this was a really, really basic logarithmic regression model. And it was basically just to determine, could I detect with any form of accuracy whether the cat was going to be in my son's room or not? And if you've never done this kind of thing before, it's actually pretty straightforward. This is like literally 20 lines of Python code. You split your data set into 2 sets. Most of it's a training set. You pass it through a model. And then the remaining data you use as a test of whether your model is accurate or not. So you train the model with most of your data, and you test it with the rest of your data. And here I was getting about 88% accuracy. So I was getting a sense that this model was relatively good at predicting this very, very simple case.
So what partition you have within training and test?
So the question was, what's the split between training and test? I was choosing 80-20. So 80% of it was being used for training the model and 20% of it was for validating the model. But that gave me an idea that this was on the right path, and then I wanted to get a little bit more elaborate with the actual mechanism. So I started deriving some features. So I had a bit of a theory here that things like hour of the day and things like day of the week were going to be good features to train a more sophisticated model on. So hour of the day is pretty easy. You can just work out what the hour of the day is. Is it raining is a bit harder. I just sort of arbitrarily chose that if the humidity was above 90%, it's probably a signal it's raining. So these are derived features. And then I could use something a little more sophisticated. I'm up for 30 lines of Python code, not just 20, to use essentially a bit of a random forest thing. And this is actually good because one of the things with a random forest is that I can actually use the testing model not only to predict the accuracy, I can actually lift out the most significant features. So even if I had a theory that hour of the day or raining or day of the week was a significant feature, I can actually ask the model to validate that for me. So using a visualization technique, I was actually able to ask the model which is the most significant factors within this decision tree. And it turns out that hour of the day was the most significant thing in actually determining the location of Snowy. The second most was outside temperature, then day of the week, indoor temperature. Turns out is raining is a really, really bad indicator of where my cat is. And I've got a bit of a hypothesis I'll share with you later about why that is. So that gives me an idea about both the accuracy of the model and the things that are driving the model. So I can actually then start generating things called decision trees. If you've never seen this kind of thing before, it's basically, I mean, this is computer generated, but you can actually, as a human, generate this kind of thing. It's basically just an if, then else, and then drop down to the next level. So here's a simple if, then else. If the hour of the day is less than 7.5, go down the left arc. If it's not, go down the right arc. Now, I didn't generate this decision tree. A model generated this decision tree. But what is super interesting is that the model determined that the top of the decision tree, and at the bottom of the decision tree is where Snowy is. The top of the decision tree is really interesting because it turns out that my cat likes to sleep in my son's room, and guess what time my son sets his alarm in the morning? 7:30. So the model has actually worked out from the cat's behavior what time my son sets his alarm clock. Another really interesting thing was in this bit of the decision tree is day of the week. It turns out that a really significant thing in that part of the decision tree is Monday, Tuesday, Wednesday up to Friday goes down one part of the decision tree. Saturday and Sunday goes down another path. So again, this is intuitively feels about right. So that gives me a model. And now I actually want to take that model and actually do something with it. Can I actually build something on top of this model to actually test and actually predict where Snow is going? So I don't know if you've ever come across Streamlit, but I suspect you're going to hear more about it. It's an open source Python library for creating and sharing web apps. It's super straightforward. And I'm not a data scientist, but I know how to copy and paste. I can copy and paste essentially those lines of code on top of the model I've just generated and generate myself a really funky web app. And I'll show it to you in a moment. It's actually really straightforward how quickly you can go from model to producing a web app. And it's not just me who thinks that's cool. Snowflake just bought them for $800 million. So I suspect very soon we'll see some Streamlit magic in the depths of the Snowflake console. Anyway, so this you can try right now. This is the application I've just generated. And if you actually put in the parameters of my home now, the time of day, the weather temperature, you'll actually find there's a 68% chance that my cat is actually on the dining room table now. And I texted my wife before and I asked where the cat was, and she said on the dining room table. So this is actually working pretty well. But yeah, by all means, you can use this model at any time and work out what the likely chance of where my cat happens to be. So that gives you a bit of a sense about how I'm wasting my time during lockdown. But I've learned a few things on the way. Firstly, I found that this stuff is actually super approachable. I went from not calling myself a data scientist to pretending I could say the words logarithmic regression pretty quickly. It's really approachable. I went from a sort of an MVP to a random forest pretty quickly. But it got me thinking about some of the things that I might have missed. The recent floods got me really thinking that there might be a change of behavior when my back garden is underwater, and I don't really have a feature for flooding yet. I also have a theory that when I'm working from home, it also changes the cat's behavior, and I don't have a great way of working that out yet. It also got me thinking, are cats actually predictable, or are they just an unknown source? Anyway, so in the end of the day, this is an ongoing learning project. I'd love to get feedback around how this is going, or if you've got any ideas about how I can improve the accuracy of cat prediction. And with that, I'd encourage you to follow along. That link will show you all the code. It also gives you some data, so you too can be training your own models to work out where my cat is. Thanks very much.
That was awesome. All right. Any questions for Simon? Then we'll jump out in at once.
Let me get the copy of your presentation.
Yes, you can have a copy of the presentation. I will put it at the same link. Cool. Oh, and by that, there's also a blog post that explains all of this stuff at that URL. So yeah. Sorry, there was another question? Sorry? Did you need that much data?
Sorry?
Did you need that much data?
My day job is data engineer, so I'm always going to say yes. So I needed that data and so much more. Cool, cool.
When did you capture the data?
So I started this project back in October and then made some errors on the way. So I think towards the end of October was when I started capturing the data with any...
Notice any seasonality?
Yeah, that's a good question. Yes, but I haven't really accounted for it yet. So I did actually try some experiments where the day, month of year was a significant feature, and it kind of just, it wasn't all that telling. So yeah, good question though. How much data in total? I think it was definitely coming up to 800,000 rows of raw data. I can't actually remember, but yeah, lots. A remarkably large amount for a silly project, I've got to say. Cool, cool. Hey, thanks so much. Have a look, follow along. Oh, sorry.
Yeah. So, like in this one, you focus more on the weather conditions and stuff, right?
Yes.
So instead of focusing on the weather conditions, is there a way, like, predicting the face of the cat based on the people around it, like? The
Okay.
way you said, right?
If I've got another 20 minutes, I'll explain the next phase of this, which is location of humans in the house. But you've already seen where this is going, is does the cat show any affinity to people in the house? So that is actually data being captured at the moment. Good question.
Follow-up presentation.
Sorry?
Did you have a chance to predict?
I haven't captured enough data to work out if the cat has an attraction.
Cat usually sit at the one corner and they like to sit where the people are around.
That we,
And the people they
I don't have enough data to back that theory up yet. I'll let you know. Cool. Thanks so much.
Round of applause. Thanks, Simon. All right, so we've got our next speakers. Feel free to come up. We'll just do the live stream and carry on with the talks. Simon, did you want to hand over your lapel mic?
Oh, yeah, sure.
Get a chance to Zoran if you like, and I'll hand over mine to Ari. So both of these folks are at Nearmap. Nearmap, if you don't know, is like this awesome mapping company. They, I think, fly around like aircraft, take high-res images, and, they're kind of like Google Maps, but more better. Is that a fair estimation, or no?
Yeah, much more better.
Much more better. Much more better is the official marketing tagline of Nearmap. And if you wanted to become a Nearmap engineer, there is this amazing DataEng hack where you can do some amazing hackathon data engineering and stuff like that, which may or may not get you an awesome role at an awesome tech company here in Sydney. But tickets are $50. We're sponsored by all these amazing sponsors, and it's all super amazing. And I'm just going to keep talking. Yep.
I'm sharing on the stream.
Cool.
But that's
Nick,
not on the...
yeah, so you're sharing your screen, are you?
Yep.
Cool. And Nick will add that in. That should be all good.
Okay, cool.
Yep. Fantastic. I'll hand this over to you if you wanted to clip on. All right. Thanks for your patience, folks. We're back online.
We'll wait for the screen, I guess. Do you want the chair?
No. I'll stand.
Oh, it's not. It's not showing up.
Still not up there.
Sorry, folks.
Cool.
Can you? Yeah, can't really see it. Thinking.
Yeah, I think we're up. Oh, it's here.
Hey, here we go.
Oh, cool. Awesome.
Cool. That's so good.
All right.
Awesome. Thank you everyone for coming, and thank you for hosting. We are colleagues from a little company called Nearmap here in Sydney. This is Ari. Ari is a principal data systems engineer, and my name is Zoran. I'm the senior systems engineer at Nearmap. I had to check that on the slide.
Still true.
So I just want to tell you a little bit about Nearmap, in case you haven't heard of us before. Nearmap is an Australian tech company which has been founded about 12 years ago in Perth. And the idea behind Nearmap was to try and make aerial imagery data available, not on demand, but whenever you need it. As you can imagine, flying airplanes is quite expensive. But we do that on a regular basis. So we take some airplanes, we mount some cool cameras to them, and we fly around quite a lot of areas, focus on populated areas. So we do Australia, New Zealand, Canada, and US. But we don't just capture this imagery. There's a lot more that we do with it, imagery afterwards. So the company's kind of, you can think about it being put together out of these various teams. And we work as a little bit of a pipeline to deliver location intelligence products. Our focus is really to be the leading location intelligence company. So we have a camera systems team who build their own cameras, and we're just in Barangaroo. So when you come to work, you walk past the labs, the optical labs, the mechanical labs, the electrical labs where these cameras are built. When they go on the planes, we have a survey operations team that organize the flights all over the world. And you can imagine how complicated that is. Weather, rules, other airplanes, restricted airspaces. When we fly these, what we call surveys, then that huge amount of data goes to our vision systems team, and they do some really, really interesting stuff with all that imagery. They stitch it all together, they stretch it to look right, to line up, to be exactly represented what the world looks like. That's where the, after that is where the AI team comes, and that's where Ari and myself work. We try and derive some real facts about the world from this pure imagery. And I will show you a few examples of what that is in a moment. And then we have exposed all that cool AI data and vision data through the APIs, and we build some cool apps with our apps team. So here's an example. Kirribilli. So this is one of these images that's been shot from the airplane. There's actually lots of images there that have been stitched together and stretched out and color corrected and made all to look like a single shot from the air. And this is where the AI team comes in. We put in all these layers over the top that represent the real world. So here, just as an example, we have roof and solar and pools that we detect using machine learning. So you can see the pools in the blue, and and you can see different types of roofs in this pinkish color, and there's some yellow there that you can see solar panels around Kirribilli. But we do lots more than just swimming pools and roofs. So we have quite a complicated AI data processing pipeline that is constantly growing, and we're adding more and more capability to recognize more and more things in the real world. So things from, type of surfaces and vegetation, all the way to picking up power poles. And when I started Nearmap, it was really interesting me having a look at how many power poles I would find in an image, and then letting our neural network have a look, and it's way better. It's way better than me. So we're constantly adding more and more of these layers to our neural nets. So how did we get there? I guess as the AI team. So if you flick to the next slide. So AI team is only about 4.5 years old. There's so much of this data, and AI team started with this very, very first version of object recognition, and they were picking up mostly some swimming pools and doing a little bit of a trial, how well it works. 4.5 years later, we're like 25 people. We have lots and lots of customers that we have to version our data processing pipelines and all our data so that downstream customers can depend on it and plan for changes. And you can see how we've gone from very, very crude kind of recognition to very, very fine precision. Yeah.
Just a question, like it can be not correct question because I'm just quite
Sure.
what you're doing. So when you capturing the images, is that only method to capture for your processing through airplanes, or it can be done by satellite imaging or something?
We do airplanes because we find airplanes have that right balance between giving us really, really good quality, but still lots of data so we can cover quite a lot of area.
And
so
that's the only way, or we can opt for other options also?
We just do airplanes.
Okay. And
Yeah.
can I ask you what other options we have to let it happen?
Or in Nearmap or in general?
In general.
Oh, in general. So I think you can do satellite imagery. That happens quite a lot. That's what Google Maps do, I think. And then I think that there are probably companies out there that might do drones, but they will be quite specific where you kind of say, I just want this construction site done. And I think Nearmap's proposition is that you don't have to pay this really, really expensive survey of one location. We will fly these areas. Like we fly Sydney, whole of Sydney, every couple of months. So you can see what's happening. Yeah. So a little bit more cool stuff here. So we do all these layers. We put them together about what could be interesting for a certain business proposition, business value. So for example, we sell these APIs as packs, so like a construction pack. We can go in and we can recognize buildings under construction. And we have a look and we know what areas they cover, and we know how accurate our model is, and that comes really, really handy to the downstream customers. The really cool thing about this is that if you see the area, our imagery is measurable. So it's been stretched out and made correct so that you can measure on the screen and you know exactly that's what sizes of things are in the real world. Another interesting one, construction cranes. Not an easy one to find, but some customers find it quite handy, and we have very, very high accuracy with picking up construction cranes in this mess that is a construction site. Cool. All our stuff is via API, of course. We serve all that so that customers can integrate downstream quite easily. So imagery and AI predictions. So this is like a little bit of an example of what you could do with our data. So for an area of interest here around Kirribilli, you can see we've got vegetation and roof. roof condition, type of the roof, is it metal or is it tiles, swimming pools, solar panels. Yeah, we've got over 100 classes that we can make really, you can tell an interesting story. And just one more example, just to show you, for example, we have a difference between a general water body and a swimming pool. The models can tell the difference. And for example, solar panels, quite precise polygons that we build. So yeah, if you consume our API, you can get polygons out of that. We'll talk about a little bit about that. Ari will tell us how that all happens.
All right. Yeah, I'll take over that. Right. So you saw all the pretty pictures and what the end product looks like. And let's talk about how do we actually get from images all the way to all the cool polygons. So if you go to the next one, it's all based on this particular deep learning process, which starts from you take a feature in the world and you define it. You start by saying, I care about roofs, or I care about swimming pools. And then you start to define, what does a roof really mean? How do you label it? Where can you find it? And then you start by sampling the whole area of the world that we capture. And then we find places where we think we might have instances, negative and positive, of that thing. So we take that class, we try to sample it, we then run it through our labeling process. We have quite a extensive labeling team and a labeling system that allows a huge workforce of expert human labelers to look at images, explore the real world around them, and then annotate per pixel what really is on the ground. Then we bring in the data pipelines, and we build the ground truth out of all of those individual annotations. We take the ground truth, and that forms the basis of the data that we use to train our models. We run our models, train them at scale, evaluate them, do a loop, a few loops of that, see how our model is doing. Once we are happy, we release the model and then run inference at scale. So like Zoran said, we fly over 4 countries. It's petabytes of imagery, and we run our inference on all of that and produce the truth about the world using our models. During this entire process, we produce a lot of data that is useful to collect and run analytics on, so that we can then feed that back and sample even better areas and create even better labels, so the model learns even better. And so this loop then continues, and whatever feature we are concerned about, whatever class, improves over time. And we can then add more definitions and more features, and we grow in both dimensions. Next one. So to do that ML process, what would an ML pipeline look like? So we have a huge team of expert labelers. Like I said, we have our labeling tool that we run both the front end and the back end. Like Zoran mentioned, we have an amazing apps team that builds these really cool web apps, which we can then also leverage for our labeling in-house expert labelers to produce high quality training data. All of that gets stored in our label data storage, the metadata, and the actual images with the polygons. We take this information and we start our data processing pipeline. We have some Kafka and dbt and Snowflake involved, which we use to then generate some dataset analytics there. Meanwhile, we are constantly, as the labels are arriving, we are constantly producing ground truth by doing a consensus on how different labelers have annotated a pixel. And if like 5 labelers say there's a tree here and the 6th one doesn't, we figure out who is right or not. And then we produce the training data set, which gets used further down for model training. And like any other data pipeline for any other data engineering application, we manage our dead letter queues, all our error reconciliation, and then feed it back so that we continually run that loop. Next one. But we all know when we are talking about machine learning, and especially when it's a newly formed team, which is 4 years old, the applications are changing all the time as the product evolves over time. Running a machine learning pipeline might seem like that, where you're always babysitting it. Next one. So what you really want is to think about how you can gain operation vacation. So there's a concept that Andrej Karpathy from Tesla AI talks extensively about. What you really want is to not babysit the pipeline to improve over time. You want to build a data engine that can simply go over that process by sampling, labeling, training, inferring, finding exceptions, and then improving over time. So you want to build operational vacation where you are on vacation and the thing improves by itself. Next one. So I think the gist here is to think of building AI systems, building model systems, not just data pipelines. And model systems is slightly different, a bigger envelope around building data pipelines, which we'll see in the next slide. So what all things should we care about? So you should definitely care about expert human labeling, because your model is only as good as the data that you produce. And if you have better workflow management, better lineage of how the data is produced, your model will improve. But only that is not enough. You need to also think about how you train your models, how the model training can scale, how your data preparation can happen fast and in a way where you continually improve and get better. Meanwhile, you want some feedback mechanism because there's never enough data. And you want to define how our livable world works, because just saying I want to find a roof is fine, but when you have hundreds and thousands even of classes that you want to label, you need to know what's the relationship between them. How does our livable world work? So next one. Let's take a little bit of deep dive into these systems. We have our in-house labeling tool that I've been raving about. There's a little video of how that usually looks like. The labeling tasks are usually quite complicated. I'm a really terrible labeler myself. That's why we have expert humans who do this work really diligently. So you essentially draw over the image and annotate every pixel and say, what is that pixel? And you annotate multiple classes. There's a simplified example of just roof here, but you would go into more detail based on the ontology, what classes reside there. You want to make those systems scalable in the sense that your workflows of how the humans interact with this tool will change over time, as well as how you produce your labels and the lineage of the data will change over time. So you want to build a microservice which cares about human workflows. You want to have a microservice that cares about how the data is being gathered over time and how it all relates to each other. And you want to make it so that all of these tools actually support not just annotating the pixels, but other use cases, like maybe detecting changes in two images or doing labeling over time, and so on. Next one. The next piece of the puzzle is the data set preparation. And I've talked about that a little bit, where once the source of all of our information, that's our labeling tool, produces that data, we need a data pipeline that continuously and at scale produces the correct ground truth and produces all of the data that helps us understand that ground truth so that it's explorable, it's sampleable, and it's easy for our models to pick, all right, this time I want to train with this set. And then over time, that's you can actually go back in time and say, this is the this is the set of data that I use to train this model. Ontology. Our world is a really weird place. And it is really hard to define an object when it really comes to corner cases. You might find things like buildings which may not have a roof. So do you add that to the definition? That kind of information and that kind of thought needs to go into it when you're really annotating everything in the world. And you need to think about it so that it improves over time. And you need to capture the complex relationship, which is essentially the knowledge graph that we call ontology. And we need to build systems to kind of talk about it, capture it, and make it accessible in the form of a formal relationship in our systems, and also for our labelers as labeling instructions. So yeah, next one. And we need to think about the feedback loop, which I think Zoran will come in and talk about.
I'll talk about feedback loop. Yeah, I really like the idea of feedback loop. So if you remember that couple of those slides that Ari showed, where there's a little arrow that we keep going around in circles, the feedback loop is the thing that drives those circles. So the idea is to make our data sets shove as much knowledge as we can come up with in there. So not the same stuff, because you don't get extra knowledge, like we're talking entropy here. Add more good stuff to it to improve the model. So the entire machine learning process, you can think of feedback loop as placing like these little probes at different places in that pipeline, and capturing all the data that looks interesting. So labeling, training, we have inference at scale, users as well, because users come up with really interesting stuff when they look at our imagery and they say this doesn't look correct. So we collect all that data from all those different points and put it into one thing conceptually, but we try and make it discoverable and easy for data scientists to use. Then they have a look, and then we sample out of that data. So they can go and look. It's like, oh, there is a swimming pool in the middle of the ocean. Is that a good thing or a bad thing? You really have a look and you say, well, that doesn't look right. But no, it's a cruise ship with a swimming pool on it. And that would probably be a really good case to have back into the labels and add that to our data set. So the idea is just to keep this thing turning around constantly, and these data sets to be improving themselves. And this can be done with a lot of work where you have to check everything, but a lot of it can be automated, or at least made easier for data scientists.
So you are manually editing those within the data set?
So
finding the discrepancies from the reality?
So the process of finding discrepancies from the reality, we can try and automate that as much as we can. So put as much data as we can, and you can look at things like, this doesn't look right based on, say like distributions that you expect or you don't expect. There's some tricks there, statistical things that you can have a look at. But it's quite good to, have people have a look at the more difficult cases. But once they add them into the data set to be sampled, then when it goes to labeling, that's always humans going in and saying, like, here's something that looks really strange, and we'll give it to our expert labelers, and they have a look, and then they say, like, yes, it is a building, but it doesn't have a roof, or, people build round houses for some reason, and that's really terrible.
There's cases of auto-labeling where you can kind of derive some of the information semantically. So if your ontology says that a building, for example, should always have a roof, then you can kind of infer that all of the labels of a building footprint would have some roof in there. So you can add some labels automatically, but essentially you would always want a human in the loop to kind of okay that this is actually true. Yeah.
So we do this at quite a large scale. You can imagine the imagery. We fly every 2-3 months. whole of Sydney, and then you add, I think we cover like 80-90% of populated area in Australia and then New Zealand and Canada. So there's lots of data. So when I looked and I was applying for a job at Nearmap, and he said, petabyte size data sets, and I was like, yeah, okay. And first thing I did when I got my AWS creds, I went and had a look, and it was like, wow, there's petabytes of data. We have over 100 label classes, and we constantly keep adding. Over 1 million images labeled, and that is like a constantly evolving process. The models are quite sophisticated. We have an entire team of research and development who just look after the model design, and they are on top of all the latest research in computer vision, and yeah, that's quite a fascinating process as well. And then when we come to output, and that's like running inference at scale. So you get this model, and then you have to run it on millions and millions of these square kilometers of imagery. And then there's vectorization there, and derived classes, and all kind of cool stuff. So yeah, over 100 million properties with lots of attributes that are there ready to go. So how do we do this stuff? So it's quite interesting. I was expecting lots of things like a little bit more data sciencey kind of tooling, but we are very, very Kubernetes driven place. So we run all our workloads on Kubernetes. Python is our bread and butter because we're doing lots of data science work. And for some of those microservices that drive our tooling and our labeling tool, we also use Python for those as well. S3, lots of AWS. When I talked about dataset discovery, we use Snowflake for quite a bit of that stuff. So when data scientists go into sample, that's one of the ways that they can go and look at that. dbt, of course, the TensorFlow and all that stuff. And Argo, we've just kind of modernized our deployment of all the microservices layer for our labeling tool through Argo, and that's a pleasure to work with.
Can you explain us the flow of data from one system to another?
For the whole company?
For this one, the technologies that you just mentioned, there should be a flow.
Oh, yeah. So the flow. So if we start from the beginning, let's go to that's good. Yeah. So expert labelers. This annotation toolkit, you can think about that as a collection of apps. So one of the big ones is the labeling tool, where the people go and actually mark the things on the images and click save. So that's JavaScript single page application with Python microservices in the back. And we have microservices because bursty workloads, and we kind of want to separate the concerns of tasks for humans as opposed to data microservices and things like that. So that's all running on a Kubernetes cluster deployed via Argo CD, CI/CD, quite nicely done actually. And then from that point, when you look further down this way, then we have a little bit more pipeline style applications, and they mostly tie together with Kafka. Python, background running processes on Kubernetes running on AWS.
AWS, Azure is not playing a part of it, just AWS.
Don't think we
No,
have
we are
Azure at the
AWS,
moment. Yeah.
And then it's going to the Snowflake, maybe on Amazon Redshift.
Oh, so then once we create those training data sets, so we kind of do all these tests to make sure everyone's labeled the same thing, and we get those labels. Labels are images, so you can't put them into Snowflake. So we put them on S3. But information like metadata about those things end up in Snowflake. So if someone wants to have a look and say, let's find all the areas where there are roundabouts or something, they can go to Snowflake and look it up there to give them a little bit of information. So data pipelines are also running Kubernetes. We're also looking at a bit of Kubeflow, yeah, and so on. So building model systems, we see it as a little bit of a bigger thing than just being concerned about pipelines. We do quite a lot of application design and modeling of our problem systems, and data pipelines and the data engineering skills is like one of the things in our toolbox. But we really have to understand, geospatial imagery. Yeah, there's quite a lot there, kind of a little bit bigger box around the data engineering. Yeah, we're hiring. So have a look. We have on LinkedIn all our roles. Have a chat to us. Reach out on LinkedIn. But yeah, lots of cool stuff to be done.
Another question, like AWS services, you might be using SageMaker on it for image classification, if I'm getting correct.
We're a little bit too special for SageMaker. Yes, we do a lot of stuff on Kubernetes mostly. Yeah. SageMaker is one of the tools that we have. But yeah, the main things. Yeah. And that's some
Very
pretty
good.
pictures.
Well, thank you very much. You can leave up the we're hiring slide. That's always
Cool.
always handy for folks. Some questions from the audience, and a round of applause for the great presentation.
Thank you.
Simon, did you have one?
I was really interested in almost like the source. You used a lot of like visual demonstrations before from your aerial photography. I was wondering if you also had anything like depth related, LiDAR, radar, magnetometers.
No, at the moment, as far as I know, the vision systems kind of detect and understand the depth with just the camera equipment. But I think we have 3 generations of camera equipment in the play, and there are talks about how near infrared and LiDAR can come into play. But no, the imagery is it. All of the depth information. Some of our newer generation imagery comes with the depth information. So there's cool computer vision tricks that you can use to kind of predict. Oh, I shouldn't say predict. You could detect the depth just from that.
And you can think about it. If there's a building and you're flying airplane on one side and the other side, you can look at how that scene changes, and you can infer some things about what's high and what's low. Things like that. Yeah.
Actually, that was going to be my follow-up question.
Yeah. That's how I think they do it. Yeah, they're pretty clever people, the vision system guys.
Yes.
Yeah.
Yeah, it's you would hours of videos later, we are still perplexed. Yeah, it's a very interesting area. Yeah.
How much data does Nearmap store or use for your imagery?
A lot.
Millions of petabytes or
Yeah, the question was how much data do we store? I don't have an exact number, but it is in petabytes. Yeah.
The problem with it is that there's always people flying planes and bringing more.
Yes.
So it grows. Yeah,
Yes.
It just doesn't keep growing. Yeah.
And as our cameras get better, it grows even more. So yeah.
you only keep the last like flyover or something.
No, so we have so one of our core products, the imagery does go back in history. So we should have got a slide for the map browser product where you can actually look at the images and you can take a historical date and you can see how that area has changed over time. So no, we do keep historical photos.
You don't have like the retention on that.
Yeah, there's optimizations there, but yeah, well, we do sell it, so yeah, we have to keep it.
And so, I guess to describe your team within Nearmap, within the whole, supply chain, if you will, it's a bit of a data platform engineering team, is it? Where you're sort of providing a lot of the infrastructure for other teams and infrastructure for the data flows and things like that for machine learning teams to utilize?
It's actually quite an interesting makeup of the organization. So we, like Zorn mentioned in the original slide of how the teams are structured. Let me get that one up. Oh, wow, that was it. Yeah. So essentially, AI team, just like all of the other team, acts as an arm that produces product. So the AI team is quite a coalesced group, which serves and builds its own things itself. So we are part of the AI team, which would have a very diverse makeup of, we would have data scientists, we would have people who are researching deep learning model architectures. We have data engineers who are building the things in that team with them. So I think this cross-functional nature of how we work together kind of has, it produces an interesting makeup of the system, because like, however you structure your team, your systems will start to look like that. So we kind of keep it together so that it's a cohesive system end to end, because we do want to bring it back and make the data engine.
Oh, it's absolutely fascinating. Like so much amazing technology on display there. So a really round of applause once again for sharing all of those insights. Maybe grab them after the presentation. Yep. So that's it, folks, for tonight. Really appreciate all of our speakers and all of you folks for coming out tonight to share a slice of pizza with us and have a chat. We'll hang around for 10 or 15 if you'd like to have a bit more of a chat, and then we'll see you next month. Next week at Safety Culture, which is in Surrey Hills in their brand new offices on Pavot Street. We've got a DBT meetup if you like DBT. I think both presentations mentioned DBT, so that one might not be one to miss. So thanks again. See you next time.